Okay, so we are still admitting students. Okay, thank you. Well, while we are admitting students, we can quickly go through what we have learned last week. Okay, so we talked about ion chromatography last week. And then, so this part, and we basically go through almost everything last week. Ion chromatography already mentioned about that. So it includes ion exchange, ion solution chromatography, and so on. So our focus is ion exchange. So that's why we'll just quickly talk about what is ion exclusion, right? So we see ion exclusion, this one. So, and the ions, they are repelled, right? Okay, so for weak organic acid, carboxylic acid. So, and for ion exchange, we talk about the strong cation, strong anion, so weak cation and weak anion. So it really depends on the charge on the stationary phase and also the charge of the analyte ions, right? Okay, so and the separation based on what? Based on the electrostatic interactions, and it's based on the charge density, right? So, and we talk about different kinds of the stationary phase. We talk about matrix. We focus on the silica-based matrix and synthetic organic polymer. And for the polymer, actually today, we are going to see that again. So for the side solution chromatography, we also use this polymer stationary phase, which is the copolymer consisted of polystyrene and divalent benzene. So you can see, like, depends on how many the divalent benzene so inside this structure. So that kind of determines the degree of cross linkage, right? And also that degree, the kind of defined the pore size in this rhizome. So, and later when we talk about side solution chromatography, and then so that is very critical because it determines the pore size and determines like which molecule can get in, which molecule cannot, right? Okay, and we mentioned about one of the big advantage of the rhizome matrix over silica is because it can handle a much wider pH range. Basically, it can handle pH between 0 and 14. So that is very important for ion chromatography. Why is that? Because when we talk about anion exchange chromatography, remember, so we say what is the buffer solution often used for anion exchange chromatography? Remember, the sodium carbonate and bicarbonate buffer, right? Okay, and what else? And also sodium hydroxide. If we use sodium hydroxide, if it's just 10 millimole, and then the pH can go up to 12, right? And for the sodium carbonate and bicarbonate buffer, and the pH can also go to about 10. So that's why that is way outside the pH range that silica-based based column can handle. So that's why we say the polymer-based separation column is the only option for suppressed ion chromatography. And also, I think by now all of you should know what is suppressed mean, right? So suppressed is for which detector is for conductivity detector, and why we have to use that suppressed, okay, suppressor to do that. Well, and we talk about selectivity, and here we spent a lot of time talking about, and particularly we mentioned about the charge density and the ratio of charge to the size of solvated ion, remember? So that kind of really determines elution order, but there are other things like polarability of the solute ion that play a very important role as well. So we just give some idea about affinity to the stationary phase, but it's not really fixed, as I mentioned. So it may vary for different column and mobile phase, but roughly, okay? So, and for the ionized, and then so affinity of the trivalent one will larger than divalent one and monovalent, but not exactly the same because the polarizability play a role. So that's the reason we see that iodide even have stronger affinity to stationary phase than sulfate, right? And also we say we have to pay extra attention to those like multi-charged valent ions, such as phosphoric acid, depending on pH. So it can be like hydrogen phosphate, dihydrogen phosphate, or just phosphate ion, right? So, and it have the single charge, divalent, or triple charge, and then that determines elution order, right? And also we compare the ions from the same group. And then from same group is mainly because of the charge density that play a very important role. That's why. So fluorine, radical fluoride, chloride, bromide, iodide. So the fluoride comes first, and then earlier than chloride, bromide, right? We explained that one already, right? We say that for the cations, the trivalent and divalent and monovalent, that one, so the influence even more significant. So, and then so basically, so those trivalent ones, the affinity much stronger than divalent ones, so on. So that's why, so we do the separation. So of those like ions, you have to pay attention. So if you want to separate not only the alkaline earth, the alkaline metal. So, and if you also want to separate, say, alkaline earth metal, like say, because they have much stronger affinity to stationary phase. So here you may not want to use a very strong cation exchanger. So that's why you can see the option. Often you see like for the CS12A. So this is actually the stationary phase is carboxylic acid and pyruvyl phosphoric acid. So it's a weak cation exchanger. And then so also for the eluent, you can see that this is the so MSA, right? So methyl sulfuric acid, this one. So and this is a very typical column like used for the ion exchanger, and this one is quaternary amine, which is a strong ion exchanger, right? And we see that the elution solution is quite typical, is the bicarbonate and carbonate buffer. So, and there are both of them use suppressed conductivity for that. And then so I think then later on, so we'll talk about this one, influence of ion strengths, because several say parameters really can influence that. So including besides the compound itself, and then we talk about mobility, the property of mobile phase, about the ionic strengths, the competing ions and mobile phase pH, they all play a very important role. And those one, we already talked about that, right? And then so we talk about the typical eluent for ion chromatography. So I think this is common sense. So I hope that all of you know that. So hydroxy, sodium hydroxide, and sodium bicarbonate. So they are commonly used, okay, for the ion chromatography. And each of them has this, like say, something like special, maybe you want to know, and especially when they're after they go through the suppressor. And for ion suppressor, we mentioned here first, because why we have to use a suppressor? Because we want to decrease the background noise, right? Because like we are using the ion chromatography, if you're using the conductivity detector, so all the ions, they are conductive, right? They are conductive. So that's why, so because we're using the buffer, the sodium carbonate, bicarbonate, so they are ions as well. So they conductive. So that's why you want to remove the signal from the background, from the buffer, but while at the same time, you want to increase the signal from your analyte. So that's why, so a very basic way is just using a chemical reaction to do that. So the suppressor itself can be ion exchanger column. So for ion, for ion exchange chromatography, we can see the suppressor is a cation exchange column, which is in hydrogen form. So that's very important. You know that? Because it wants to remove what? So it wants to we exchange with sodium, so in the buffer, and while exchanging the sodium in the buffer, the sodium gets on the resin, and then so the hydrogen or hydrogen ion so get into the solution, and then so it form carbonic acid, okay, with bicarbonate. So this one is a weak acid. So that's why so it's not so conductive as the ion itself, okay? So, but however, so now it converts chloride to be what? Hydrogen chloride, so it's strong acid form. So that's one, because when we talk about the conductivity, so, and hydronium ion, this one, hydrogen ion, is the most conductive cation, okay? So I think I wrote some number for you guys before, right? It's 350. And then if we're talking about potassium, the sodium, so that potassium, I think it's just at 74. Sodium just 50, right? Okay, so we mentioned that before. So that by that way, increase the signal, increase the analyzed signal, but lower the signal from the mobile phase, from the background. So that's why increase signal to noise ratio, and then so get more higher sensitivity. So, and we talk about, like, say, for the context changer chromatography, it's opposite. So it's suppressor is an ion exchanger, so in a hydroxy form, in hydroxy OH, right? Okay, because if we're going to replace so those acidic buffer, so in the mobile phase, so it replace chloride, and then by that way, so before, so the background, so the mobile phase is strong acid, very conductive, hydrogen chloride now become water, so which is much less conductive, and then so. And however, so this one, the sodium chloride from a salt becomes sodium hydroxide. So, and because of replacement of chloride by hydroxide, hydroxide actually itself is the most conductive ion. Okay, so conductivity, I think, remember, I gave you a number, is 198, right? So, and that's why by this way also increase so the signal, the response, and lower so the background, including the signal to noise ratio, increase that. So this is something that you have to know, okay? So, and have to understand that one. So, and that from that, so that's why, so you see that, so so that is the solution we use, and that we also mention that. So, and if you just like dealing with the single charged, the monovalent ion, like ammonium, alkaline, and small aliphatic amine in cation exchange. So you can use a strong cation exchanger, and using the mineral acids such as hydrochloric acid, sulfuric acid, nitric acid as a diluent. However, if you want to deal so alkaline metal and alkaline earth metal together, so like this A plus and A2 plus, so the divalent one. So, and then you cannot use a strong cation exchanger. So you may want to use a weak cation exchanger. So, and then so, because then, so that in that way, it's more easier for you to elute the analyte out. Okay, so that is basically the key points. So we talked about already, right? And also we talk about this particular issue about the why the calibration curve for certain species in IC cannot be completely linear. So that is because of the weak acid, and particularly for acetic acid and also for the hydrofluoric acid. I think we write down that one, so from equation pH equal to pKa plus log A minus over HA, right? Okay, we calculate that one. So we say that for this one, so actually the only about like less than 20% of the acetic acid can be dissociated under that pH equal to 4 condition. Okay, so and so that's the reason. So it's partially dissociated when it has even higher concentration, and then the solution get even more acidic and even more difficult for it to associate. And then so if it's not fully dissociated, so and then that influences response, conductivity response to its concentration, because the ions actually conductive. Okay, we want to be the ionic form, not the neutral form. Okay, so I think we stop here, right? Okay, so there are so different factors so that can influence so the IC separation, right? So including the pH, salt concentration, salt gradients, flow rate, surfactant, and organic solvents. Particularly, we mentioned about methanol and ACN, right? Okay, so we still remember. So we can see here. Sorry, we quickly refresh that. And we can see with addition of ACN, so that actually was more ACN added, so that reduce K value. That means let it elute faster, okay? So, and methanol is the opposite way, okay? So that's why, so those are the parameters that can influence actually. Okay, so that's a line. So, and then, so here, you see. Okay. Yeah. So that's why we see there are different factors that really influence the pH, salt concentration, salt gradients, so flow rate and temperature. And here is form shows some of the troubleshooting of ion exchange. So there are different symptoms and they may have different causes. So this one just give you some idea about so what kind of problem you may see and what could be the cause and how you can solve that. So if you're using a new column, and you see a very poor and n value, so that's it's not really so high efficient, very poor peak shape. Something like you can think about is it possible like you injected the sample is too concentrated, so then you can need to do the dilution. And maybe it's possible like inject the volume is too high, and then so or maybe it's because like say your sample has been there for too long and it contaminated. And also how about the joints? So are you using a wrong size and make the dead volume to be really large? So that's also something that you think about because they say if it's new column, so its size itself, then the column itself like so should not be like really decayed, right? Okay. So but if it's poor plates on the used column, and then so also you want to like say check those one first. And then so maybe it's because the column itself, like say, have the column conveiling. And then so and you may want to wash like following the recommendation, or you can even use some acid to remove those ionic molecule and so on using the organic solvent. So to remove hydrophobic molecule and so on to do those kind of things. But as we always recommend it, so you can also see that in many of the example. So for this kind of analysis, we recommend you guys to use God column, and that will greatly help the performance of your real column. Okay. So and if you have see poor peak shape for some of those samples, and then so and also is something that you can think about, and this is the solution. But how about for this two, 4 and 5? So 4 and 5 is that if your peak comes up too early, that means if the K value is too small. So that means what? What can influence the K value? What can influence that? Ionic strength, right? Okay. So, and how about the flow rate? Yeah. And how about the pH? They all right. Okay. So maybe your gradient is too strong. So, and ionic concentration, ionic strength is too strong. So then you may want to lower the gradient. So, and also you may want to use weaker salt. Weaker salt, that means it has the weaker elution power. For weaker elution power, that means the salt, the ion itself has less affinity than the one you used, right? How about for pH? Just pH. If your pH comes up too early, for ion exchanger, you want to lower the pH. What does that mean? Because if your pH comes up too early, and what is the typical mobile phase we use for ion exchanger? Sodium carbonate and bicarbonate solution, right? Buffer, or sodium hydroxide. So if you lower the pH, that means like less concentrated for this, if you say sodium hydroxide. If you lower the pH, that means make it from pH equal to 12 to 11. So that means you have less OH, right, ions inside. Of course, then that will be, say, less elution power. And then so that can make your peak comes out later, right? Okay. So if you're using carbonate and bicarbonate buffer, if you lower the pH, and what happened? No, the pH, and then so there will be more bicarbonate ion instead of carbonate ion, right? Okay, carbonate ion has 2 minus, bicarbonate ion just like 1 monovalent, which have a stronger elution power, the carbonate ion. So if like now you lower the pH and become more bicarbonate ion that part, and then so now it has so weaker elution power. So definitely your compound can retain them for a longer time, right? Okay, so that's easy to understand in that way. Okay, so how about your peaks come too late? That means like you're not having enough, like say you have the K value too large, you want to speed up, and then you want to using a stronger elution power. So you want to increase the gradient rate, you want to use stronger salt. Another way you can do is that you can also use like say the pH, of course you can adjust a little bit, and also like say reverse way, like this one can be like higher for ion exchange chromatography. At the same time, so you can also use like add a little bit of organic modifier into the mobile phase. So we know, let's say ACN, so can help elute. But this is particularly more used when you're also analyze some inorganic and organic ion together. So, and some of the organic ions, like say if using ACN, can maybe easily or help them to come out faster. Okay, anyway, so you'll run a gradient, right? Okay, so now we're going to see some sample as a wrapping up of this chapter. Okay, so we can see that ion chromatography can be applied in many different fields. One of that is in environmental science, and it's commonly used for water analysis. And here shows the analysis of the water, so in pond water. So, and then you can see here is the standard. So fluoride, chloride, nitrate, so hydrogen phosphate and sulfate. And this is what we see in a pound, okay? So this is AS14. So this is pretty typical column used, we just mentioned about. So this is strong quaternary amine, right? So I used carbonate buffer, bicarbonate and carbonate buffer for that. And also suppressed conductivity. So everything you know. And how about cut time? Of course, same for cut time. So here's same for the standard and pound water. And then, so this is CF12 because it has, so magnesium, calcium together with those monovalent ones. So that's why. So using a weak context changer. Okay, so elute can also be like sulfuric acid is fine. And then, so you suppress conductivity. And this is another analysis that used for personal care product. So, and you can see fluoride, chloride, sulfate. Okay, so, and this is the phosphate. I think 5 is the phosphate. So orthophosphate actually, what mean here is the phosphate. Oh, I think it's 3. Yeah. And this was citric acid, right? We already mentioned about this. So this is something like say C6H5O73 minus. And then so this number 9 is tripolyphosphate. The tripolyphosphate is something is for your information. 4 minus. Okay, so you can see that this column is AS11. This one is actually also a alkyl quaternary amine. This AS11 column is often used together with sodium hydroxide. Sodium hydroxide. But you can see normally we just have 10 millimolar sodium hydroxide, which is pH equal to 12. Now it used 200. Okay, but of course it's diluted just like 40%. But about 40% here is about say 100, let's say that. And then so that is actually already about pH, say equal to 13, right? Okay, so it's pretty high, okay? So pretty strong. So because actually it needs to elute those trivalent or quadrivalent one to come out. And then so it's also used as suppressed conductivity. So it runs the gradient, you see that. And this one is also another analysis for the separation of this this one. So salicylate. Okay, so this is an acid. Okay, so and let me see. Just give you some structure information. Okay, so and we can see it has A, B, C. Oops, it has A, B, C. So A is water, B is again so sodium hydroxide, and again is AS11. So you can see you also use Scott column, see that, and it runs gradient. So and in about 20 minutes, so it's starting from 2 minutes to 20 minutes in this range. It's great, gradually reduce A, and same time, so increase B, sodium hydroxide, and also it has C, which is ACN. So the ACM, because you see, and this is chloride, phosphate, citric, and thing is just try to help to elute. So this the salicylic acid come out, okay? So because this one is the more hydrophobic structure, so addition of ACN in the mobile phase may help the solution of those one in the mobile phase, and then comes out. And this is analysis of beer. So, and actually it's a lot of the sugar compound, glucose, fructose, and then so metals and so on. So with the increasing chain, but you can see that. So, and also it use sodium hydroxide. Okay, pretty high concentration here again. And then so it's pretty interesting. And also the detector now is not conductivity, but it's based on current. Okay, so it's pulsed amperometry. Okay, so and it's also electro detector. So what else? So yeah, and also again, so you can also analysis of those acids, carboxylic acid in a sample. So and this is a separation of again acid in the British stout. Okay, it's the kind of beer. So and using the ion exclusion, okay, ion exclusive chromatography, so not exchange, because now it is analyzing those carboxylic acid. You see that? Okay, so that's why. So you use, so it's perchloric acid. So it's a pretty strong acid, right? So this one's much stronger. So than those acids. So this one again, so the stationary phase, so it's sulfonate. So the counter ion, right? So sulfonate, and then so this one, and also so many of the hydrogen here, combine that one. Okay, so not really. So this one. So we can go back to see that one. So anyway, as we show you guys. So anyway, so and the one is the diluted strong acid. So it's the ion exclusion chromatography for this one. And again, so the detector is also for that current. Well, anyway, so that is basically how that so IC is applied. So now we're going to go to the next chapter, so which is the size exclusion chromatography. Okay, so the size exclusion chromatography actually is a very easy chromatography. It's a little bit different from what we have learned so far. Okay, so what happened to it is, so the size solution chromatography, as you can see, so from the name, so the separation is basically different from all other chromatography we just mentioned about. Because separation is based on a simple molecular size classification rather than any of the interaction between the analyte and the stationary phase. Because we talk about the reverse phase, normal phase, partition chromatography. Like for reverse phase chromatography is based on the hydrophobic interaction between the analyte and stationary phase, right? Okay, so and we just talk about ion chromatography. So for ion chromatography, so the stationary phase and also the compound, they should have opposite charge. So and then so the analyte can be attracted to stationary phase or retained by stationary phase by the electrostatic interaction, right? But here for the size solution chromatography, it say no, I don't want you to have any interaction with the stationary phase. No. So the separation just based on the molecular size in solution with respect to the point size of packing. So here you can see two sizes mentioned. One is the molecular size of the analyte. It's actually the kind of hydrodynamic volume because it's so weighted again in ion. Okay, so and molecule also as well. Okay, and hydrated molecule, and then so and also the point size of the packing. So the size of the molecule and size of the point size kind of determines so where the compound how much like volume or how much time does it take for the compound to come out. Okay, so that's why so we have to use a porous material. as the column packing, the porous one. So because here mentioned about the pore size, okay? And then so what happened, as you can see already in this figure, so because the porous material and the pores have the micropore and macropore different size, and then for those pretty large molecule, so it's too large, so it cannot travel into those pores. So the only volume for them to come out is the volume between the packing particles. So they are totally excluded from those pore areas in this stationary phase. So they comes out first. However, for the small molecules, because they're pretty small, so they can diffuse into the pores. So they have a longer path, a longer retention time. So then large molecules, so they comes out lost, right? Okay, so here you can see that. So here inside the porous stationary phase, there are the stagnant mobile phase, right? Stagnant mobile phase, stagnant. Okay. Mobile phase we talk about. Okay, so now the mobile phase, but now the mobile phase is just like a solvent. Okay, and then so as the diffusion is the only way for the small molecules to get in and get out. Okay, if the small molecules like take enough long paths, so you really want the molecules to have a good diffusion, a fast diffusion rate in, so it can diffuse in and diffuse out, and then it take longer paths, right? Okay, to come through. So and then so therefore you can see here no interaction between analyte and stationary phase is wanted. No. Okay, so everything based on the size, separation based on the size. The larger the molecule, the faster it comes out, and the smaller the molecule, the like say slower it comes out, like that one. Okay, so that's very easy and straightforward, right? Okay, so you say that's the end. No, so we're going to talk about the more about its application. Okay, so but principle so easy to understand. So here just give you a more like straightforward illustration about size solution chromatography. Now we just like give the large molecule and medium-sized molecule and small molecule different color. You can see for the large molecule now it has color of red, right? So the enter few pores in the gel, or even if it's too large, it's totally excluded. So it travels, it comes out first. For the very small one, like the pink ones, okay, so they enter many pores in the gel, equilibrating between the gel and moving buffer. So they travel slowly and then elute later. Okay, so and how about the medium-sized one? So they can enter some of that, you can see here, but some are too small, they cannot get in. So so they comes out in medium. So that is easy. So well, for the size solution chromatography, it can be generally subdivided further, so into mobile phase category. So depends on. So and for example, we have two subcategories for this SEC. One is the gel filtration chromatography. The other is gel permeation chromatography. So for GFC, so its mobile phase is an aqueous buffer. Mobile phase aqueous buffer. Okay, so it deals with the sample, so that is water soluble. For example, protein. Because one criteria for the mobile phase in SEC is the analyte should be completely soluble in the mobile phase. Because now the mobile phase is not really something like say want to have some distribution between the analyte distribution between the mobile phase and between the stationary phase. No. So the mobile phase just carry the main task for the mobile phase, just carry this molecule to go through the column. That's it. It's a solvent. The function will just dissolve the analyte, making them in a solution, and then they can go through the column. So basically, for compound, as long as they can dissolve in the mobile phase, they can be eluted. So in SEC, okay? So that's what happens. So that's one. So for geofiltration chromatography, mobile phase, aqueous buffer, okay? And so therefore, it deals with those water-soluble compounds, such as proteins. And for gel permeation chromatography, this is one we often see. So And for polymer analysis, GFC is for more biological sample, like protein analysis. For GPC, is mobile phase is organic solvent, such as THF, often used for polymer, and also something like, say, methylene chloride or dichlorobenzene, so those chlorinated compound, the solvent, or sometimes even toluene, ethyl benzene, or sometimes cresol are used. So those are the typical solvents are used for gel permeation chromatography, and then to deal with those separation of those compound that's soluble in less polar organic solvents. Okay, so that's a polymer. So these two, okay, you will see that. Now you should know the difference. What is gel filtration? What is gel permeation? So what are the difference of these two? Okay, so of course, then the stationary phase will be different because the mobile phase have to be compatible with your stationary phase. So in gel permeation chromatography, because now you are using organic solvent as mobile phase, and then the mobile phase supposed need to swell, so the stationary phase. So that's why the stationary phase need to be something like hydrophobic material, right? Okay. So, but for gel filtration chromatography, the stationary phase, because the mobile phase now should be compatible with stationary phase, the stationary phase should be more hydrophilic, should be like, so that was more polar one. Okay, so you'll see that very soon, but just some idea now. So therefore, so we can use size chromatography for separation of biological macromolecules, those soluble in water, such as protein. So we can, another very important application for that is we can use this one to determine molecular mass and molecular mass distribution of polymers. Okay, so that is the big application for this one. So why we have to do the molecular weight distribution of polymers? So what is the polymers? Polymers, so you can see they have a distribution of various chain lengths. For example, later on you see that. So for example, the polystyrene is the one, so that is the commonly used. If I have structure for this one, C4H9. Okay, you can see here, depends on the n number, With increasing n number, so the chain length increase. So the molecular size of the polystyrene increase, and then therefore molecular weight. Okay, so that means when the size increase, the chain n increase, so the size increase, and then so molecular weight also increase. Okay, so depending on different n number, so the polymer, so it has the different molecular weight. How about for the monomer? Monomer, it just has one single molecular weight. So they are molar dispersed. Okay, so not that the polymer. But why we care about the polymer, the molecular weight? Because it is important. It kind of determines the physical property of the polymer. For example, so the temperature, the polymer often produced for industrial use, right? Okay, so and the temperatures for the polymer to have the transition from liquid to wax to rubbers to solid, and that is determined by this molecular weight. Okay, so and also the molecular weight can determine mechanical properties of the polymer, such as the strength, the toughness, and viscosity. Okay, so if the molecular weight is too low, so the transition temperatures of those mechanical properties, so will be generally too low for the polymer material to be, like, say, useful application for this commercial usage. Okay, so that's why, so it's quite necessary to determine so the molecular weight of the polymer, because you don't want it to have the reagent, or when you manufacture the polymer, you want to have enough large, enough high molecular weight, and to have this enough physical property. Okay, so that's the reason for that. As you can see here, so basically, and what you can get from the size solution chromatography, you get some distribution like this one. So it looks like, so the distribution of molecular weight, it looks like envelope, so of elution from a column set. So onto that, you can see this multiple peaks for that. It corresponds different n number. So now we have point X, point Y. Okay, so can you guys tell me, so which peak X and peak Y, which one has the larger molecular weight, X or Y? Which one? Which one has the larger molecular weight, X or Y? Think about it. Which one comes out first? Which one comes out later? The big one comes out first, or the small one comes out first? Think about it. X first, right? Okay, so X first, and then, so which one is larger? The larger one comes out first, or the smaller one comes out first? This, now we talk about size solution chromatography. Because we say the size solution chromatography, the large molecules that totally get excluded. Yeah, so the large one comes out first. So that's why. So X actually is the larger molecule, so than Y. Understand? Okay. So this one. So and then so it comes out first, and then so it has so a smaller elution volume. Okay. So thank you for your response. So very good. Okay. So and yes. So and then so here is what we need to do. You can see that from that we can get idea about that, because actually it's based on separation is based on molecular size. But however, so for the same group compound, so the molecular weight increases together with molecular size. So that's why, so we can have this one, so indirectly relate the elution volume, this one, to the molecular weight. Okay, so you can see the differentiation and separation only occur over a certain range of molecular size. Why? Because it depends on the point size of the stationary phase, right? Okay, so it's not say whatever you inject, they can be separated. No, it depends on the point size, the range of the available point size for it to diffuse in. Okay, so if the point size is too small, so most of the molecule cannot diffuse in, they just all eluted, so at same volume. So if they have enough range for that point size for the column, and then so it will have the better separation ability. Okay, so and typically according to the availability of the different range of the point size. Okay, and then so you can typically so separate molecules weight of 2,000 Dalton to 200,000, so 200 K Dalton. So and however, so if this one can increase to even larger one, 1,000 K Dalton. So by use of more specialized gel, I mean, like if it has, because it's large, right? So if it has the macro pore, so okay, macro pore, right? That means this pore size large enough, and then can handle the large molecules, right? Okay, so let's take a look. So and for those very large molecules, they cannot diffuse into the column. So the volume or the area that they can travel through is the free volume outside the packing particles. Okay, so which is called the void volume. The void volume V0, all those volumes outside the packing particles, because now the size solution chromatography, they're also packed column. So they also have those, can be silica gel or can be resin. Okay, so those particles, the diameter typically say 5 to 10 micrometer. It's similar, okay, at HPLC, but then so they have the gap they have the areas between those particles. And for the compound, for large molecules, for very large molecules, so if cannot diffuse in, so V0 is the volume, so they can go through. So, and so the space, just the space outside the gel particle, okay? The space between the individual, say, stationary phase particles. Okay, that's just the only space available for them. So, well, how about for the small molecules? Well, for the small molecules, very small one, that can diffuse because each of this one is actually the porous one. So they have the pores, okay? So they're porous, they're not really solid like this one. So all of them like this one, okay? So very small particles. So the molecules, they can diffuse into the pores. So that means the volume for them to go through is the total volume inside the particle and the volume outside the particle. So that'll be the pore volume plus the volume outside the particle. So they will take the, how about I say largest, for the smallest. So they were going to take the total volume to comes out. The total volume to comes out, okay? So, and well, the difference between VT and V0 will be the volume, so of the pore volume, that'll be the pore volume inside stationary phase. It's very difficult to directly measure the pore volume, right? So it's very hard, you cannot do that. So that's why it just roughly estimated. The estimate of the pore volume inside the stationary phase roughly equal to VT minus V0. Okay, so what happens, this VI actually is very important. So this VI kind of determine the capacity of SEC. So why say that? You'll see. And the retention volume, VR, so it's often used in science chromatography instead of the retention time, because this is the retention volume. So you can see here, so that's, so it takes for them to come out. So that's why instead of have the chromatogram, so what you have is, we call that elution profile. This is an elution profile. In SEC. So it shows that, so the sample, so x-axis is elution volume. It can be elution time as well, but most of the time it's just using elution volume, okay? Volume. And y-axis can be absorbance if you're using a UV. And normally if you're using a UV and no absorbance, so it's like 220 or 280 nanometer. So for protein, and then so it will be like say 254 for many others, okay? So for others, but however, for many of the polymers, actually they do not have this UV chromophore. And then what happened is, so here y-axis not necessary to be UV, okay? It can be something like mass-based response, okay, or it can be like refractive index, okay? So mass-based one, anyone still remember? We actually introduced one. So we're talking about HPLC. Okay, so just remind you, ELSD. If anyone still remember, what is that? ELSD, evaporative light scattering detector. Okay, so we'll talk about that one. That one is the response to the base. Okay, to the mass. Okay. Okay, so now see that. So elution, sample injected. Now you see differences. Let's talk about this one. So for the high molecular weight one, so the largest one, they're totally excluded. So we just talk about. So the void volume is the volume they can travel through. That is volume outside all particles. So they comes out first. Okay, so they are totally excluded. So that's why they comes out here for the largest. Okay, so they are excluded. So this is the volume they do. So V0. And how about so for the molecule, so that's small enough to penetrate all pores? because the since that's mobile phase, so we say the stagnant mobile phase inside pores, diffusion is the only way for molecules to escape from it. Okay, so as a result, it comes out very late. So here is the VT for the smallest. So the diffuse into the all pores in the stationary phase, and the total volume VT will be like the volume inside the particle and also the volume outside the particle. So basically, so this one is the maximum volume it can use, right? Okay, so we call it breakthrough. Breakthrough volume or breakthrough time depends on you using which one. So what does that mean is like say, so as long as your analytes, they all dissolve in the mobile phase, okay, in the solvent. So when it comes to the breakthrough volume, the breakthrough volume indicates so the end, the completion of the separation. Because it's the maximum volume can use. Everything should come out, even the smallest one. So that's the end. So it indicates the completion of the chromatogram. Okay, is that easy? So that's why we say SEC, once it comes to VT, that's the end. It's predictable. It's something like so straightforward. As long as the compound, so they dissolve, they should all comes out. So by the time of VT, by the volume of VT. But however, you say, no, don't I see this one? I see that something comes out here. What is that? You say, oh, everything should comes out. Why I still see this one? Okay, so this is something we do not want. Remember we say that. We say SEC is different from all the other chromatography because we don't want any interaction of the analyte to the stationary phase. We don't want it. Because separation based on size, not on any interaction. But however, so that's the ideal case. So your stationary phase, sometimes you use silica particle, porous silica, sometimes you use the resin. So like for the resin, so it has some hydrophobic surface. So it may have some hydrophobic interaction with some of the analyte. So if it has this secondary adsorption, so that will hold the analyte, let them comes out after so the VT. So this is not what we want. So and then so because if it comes out, that means it has secondary so adsorption. And then what we need to do is like say, then you have to use some mobile phase so that has similar chemical structure, like say, or similar chemical property like the stationary phase. And then so and the analyte may be more soluble in the mobile phase, and then so can be eluted out. Okay, so this is something we don't want. Okay, so theoretically or ideal case, everything comes out within VT. Okay, that indicates the end. So you can see that V0, the start, right? So exclude VT, the end. So that means separation only happen between which two? The separation only happen between V0 and VT. So that means V0 minus VT is the volume available for separation. This is volume. And this is actually almost equal to the volume for what? Well, volume, so inside the pore, right? Okay. So, and so you can see that. So that's why. So the capacity of SEC is limited. Because the volumes inside pores, they are limited. They're not really that big, right? So cannot compare with those normal HPLC column. But this actually can be solved, the limited capacity, because you can put the same column so in a row, so and then that can increase VI, so right, that can increase that can be halfway probably solve this problem. But we can see that for just general speaking, so the SEC, because the VI is only volume for the separation to take place, so it has limited capacity. Okay, so that is another characteristic for it. So first, so you can see everything complete by the breakthrough volume, so it's quite predictable. And say second, because all the separation has happened between V0 and Vt, so it has very limited volume for the separation to happen. So its capacity is limited. Okay, so this is what you see here. And then so for different size particle compound, because keep that in mind, separation based on size. Okay, separation based on size. So, but indirectly to molecular weight, but separation based on size, not molecular weight, indirectly molecular weight. Okay, size. And then so this is the larger one. This is a larger size, and this is smaller size, right? Smaller size. Okay, so the larger one comes out first. So the second, the smaller one comes out later. Okay, so elution volume is a function of molecular size unknown. And for the polymer, because the size increase, molecular weight increase, so it's indirectly for molecular weight. Okay, I hope that is clear. So and you can see, so if we talk about some partition, KD means partition constant of the solute between the gel matrix and solvent, but actually there's no interaction. So it's not really a typical normal HPLC. It's not really following the Van Dempster. So that equation, no, not really. So, and then so, and we don't see really a peak broadening along that. And the property of the mobile phase so does not really influence the elution volume, because the mobile phase here now is just like solvent. It's just everything you need to dissolve it. That's it. Okay. So, and if you're using, say, you can say now you're using one single mobile phase. Now you're using a gradient. You say, I'm not using a gradient. I change the gradient. But not really change elution volume because it just carry them out. Right? Okay. So this like that one. So, and so KD, and then VE means effluent volume. So this is when, so that is instead of like say T, so retention time is retention volume. So that would be VE for the compound. Okay, elution volume of this designed compound. So that's why the partition constant can be write as VE minus V0 divided by VT, yeah, minus V0, which is VI. Okay, so and so therefore, and then so we can get that V equal to so this one. So it just like gives some idea. So you can derive so the elution volume from the relationship between the partition constant and elution volume. Okay, so probably we just enough to take a break here. So only talk about 57 minutes. Oh, sorry, I didn't look at the time. Sorry about that. So how about we take, like say, 5 minutes already 58. So we are going to come back at 20:03. Okay. So and then we continue talking about so the remaining part. 5 minutes break. Okay, so we're going to continue, okay? I hope from here now you already get some idea about what it should be look like. Okay, so I add one of this picture, but I actually updated the teacher notes because I had something like say, help you to understand more. So now this is instrumentation. It's very typical for LC system like that. Because also it's kind of liquid chromatography. You have the column here, the sample extraction part. You have the solvent reservoir, and then so some collection flask, and also you have the detector and so on. So, and if you look at the different parts, so the mobile phase reservoir should be filtered and degassed, and the pump, okay, so it's high pressure pump because you have the, again, it's a packed column. The diameter of the particles packed is about 5 to 10 micrometer, right? Typical is similar. So that's why you have your high pressure pump, but it has special requirements for a more strict requirement for the pump. It should be very precise and reproducible, and also reproducible, sorry. And also plus it should be thermostatic control, okay? So, and it should maintain flow at 0.1 to 1 milliliter per minute. So why it should be very precise and reproducible? Why particularly we point out? Let's leave it as a question, okay? So, and also it has the injector and has the column. So we talk about each of them, and also the detector, what detector it is, okay, and the data system. So here, so we are particularly focused on so the stationary phase. We'll talk about the mobile phase requirement, and also we talk about so the sample preparation. Okay, so this is 3 key parts for that. Okay, but we also talk about the detector and so on. So first, so let's look at the injector. So for the injection, you don't want to inject too much, okay? So the injection volume really can influence the measurement of the BE. So, and in ideal case, so that's what shown in this top figure. So this is the ideal case. You can see that. So the sample volume injected should be small enough to be just ignored, neglected, compared with the VT. Okay, so and then the VE is measured at the volume from the injection point, you can see from here, to what? To the peak maximum, so in the elution diagram. So that's why, so here. Okay, so that will be the VE. So straightforward, right? Okay, so however, if you somehow inject the sample size, so not negligible compared with the volume, so, and then what you need to do is about the middle point of this injection platen, this one, flat, and then go to the peak maximum. But now you can see the peak become wider. And C is not the case we want. So this is too much over, right? And if it happens, and if you have no choice, and then so, yeah, so you have to kind of like say, have inflection point, but no, we don't want this to happen. So we want A, okay? So this is a case. So, and the sample injection volume should be less than 2% of the total volume for the elution, okay? So that is the requirement for it. So there's something we care about the mobile phase, okay? So the mobile phase and the stationary phase need to satisfy some of their conditions. So just quickly, because we say that the mobile phase requirements, the sample must be completely soluble in the mobile phase. So the mobile phase is, because we have said that for many times, right? Unlike any other, say, liquid chromatography method, the mobile phase just act as a solvent. So we mentioned that its physical property does not influence separation process because it just needs separation based on molecular size, not its distribution between the stationary phase and mobile phase, right? Okay, so that's why. So the purpose for mobile just bring them away, carry them, go through the column. That's it. Okay, so that's why we say the solvent gradient even do not alter the retention volume. So because as all compound, so they have to just leave the column, so between V0 and VT, smallest V0, largest VT, right? Okay, so basically we say as long as it can be dissolved, you should be able to be eluted. Okay, so that's it. And also the sample must not interact with stationary phase at all. We say if it's happened, so you will see a peak coming out after VT, but that's not what we want. Okay, that means we don't want any adsorption or hydrophobic interaction. So happen there. Okay, so and if that happen, you say there's a way to do it. If adsorption effect happen, it can be reduced by using a mobile phase, which is chemically related to the stationary phase. For example, we can use toluene. So for that, later on we talk about the styrene divalobenzene, so colon, so that one. Okay, so and this is the second one. And also your mobile phase, you don't want your mobile phase to degrade the analyte. No, definitely not. And the mobile phase should not damage the stationary phase either. No. Okay, so instead the mobile phase should be compatible with the stationary phase. So that's why we say if you're using for gel permeation chromatography, if you are using an organic solvent, and then so for example, you're using so toluene that one, so and then should be compatible with stationary phase. The stationary phase normally it's just like polystyrene divalobenzene is also that one. So they should be able to swell the stationary phase and also dissolve all the analytes. Okay. And also when you are using the mobile phase, so you say, okay, now just a solvent, just carry that. So I guess I don't need to use such a high quality. No, still you need to use the HPLC grade. Okay, you need to high purity one because you want to avoid impurity by clogging the column. When you also then because the impurity will cause some baseline noise, you want to avoid that. So as well. Okay, so that's a requirement for those mobile phase. Okay, so if all these conditions satisfied, so and the size switching chromatography relatively trouble-free and pretty simple, and then so predictable, and then pretty fast, and then so and at this one, so you can see that in the updated so notes say for gel filtration chromatography, we say because the mobile phase now is aqueous, they're dealing with the water soluble sample. So the mobile phase usually consists of an aqueous buffer, so with ionic strength of 50 to 100 millimole. So untypical flow rate in order of 0.1 to 1 milliliter per minute. But for gel permeation chromatography and THF, chlorinated hydrocarbons such as the chloroform methylene chloride, and aromatic hydrocarbons such as benzene, toluene, and M-cresol. So they are commonly used, okay? So because they need to dissolve what? They need to dissolve the what? The analyte, which is soluble in less polar organic solvent. Okay, so that's it. So, and also something like say, because it has small elution volume, so and we try to avoid any of the extra column volume. Okay, so how about now we come to the stationary phase. Stationary phase. So and again, so use small silica or polymer particle, so containing a network of uniform pores. That means using porous silica particle, using porous polymer particles. Okay, so they have the pore size can be well defined, and then you know so what kind of molecular size it can handle, right? So better color efficiency and separation can be attained with small particle packing. That means when DP again here, so if it's a DP decreased, you get better N. So why is that? Because that is like say if we have a column, so if you have very large one like this one, so you only have limited number of particles. You have very small ones. Yeah, they'll be well better packed, right? Okay, so actually they will have a smaller V0 and they will have a larger VI. Okay, if it's DP decreased, more well packed, and then you have a smaller space between those packed particles, and you will increase BI, so porous And then so that's why, so it's, remember we say that VI is the available volume for the separation to happen, right? So, and then the capacity will increase, and then so you get the better separation, right? Okay, so that's it. And also, diffusion is the only way for the analyte to come out from the stagnant mobile phase inside the pore. So you want the molecules, they can have high diffusion rate, and then so it can easily go together with the mobile phase, right? Okay, so there basically, if you're talking about the stationary phase, the composition, so two types of the stationary phase. It can be either porous polymer beads or porous silica-based particles. Okay, I think this two we already talked about very similarly to in the ion chromatography. That should be something like, say, not that, say, strange for you guys. You must be, like, say, familiar with that. So first, how about the porous silica based particles? So the pore size is ranging from 40 angstrom to 2,500 angstrom. That is the 4 nanometer to 250 nanometer. Not really a really wide size range, right? Okay, so it has its own advantage always for silica particle. We know that it's rigid. Okay, and so it's rigid, so that means it's very easy for packing, easily packing, and also it can handle high pressures. Okay, and also it's has more rapid equilibrium with new solvent. So it's kind of the stability, this kind of ability let it to have the use of a wider range of solution, even include water. So even including water. Okay, since including water, we think about, okay, so that means it can handle with aqueous phase. That means the silica, pore silica particle can use for what? Geofiltration chromatography. Okay, can use for the separation of those biological samples, can use for the separation for those water-soluble samples. And also it has the stability at higher temperature. But however, we already know that for all the silica particle-based one, they always have the limitation is pH range, right? So they have to be within so a certain pH range. But also, it has its own absorption effect. We mentioned that before as well, because the silica particle itself is polar, so it has the Sandalone group. So this Sandalone group they have those absorption effect, particularly for the separation of those biopolymer. So that is highly polar. And then for that one, so and then you may want to do some chemical modification and of this Sandalone group to be like less polar. And also it's possible that this silicon-based particle then can catalyze some of the degradation of the molecules, especially those polar ones. But this one, so is relatively hydrophilic. Okay, so relatively hydrophilic. So and another choice is cross-linked polystyrene divalobenzene. Okay, this one is our old friend. We have seen that before, right? Okay, so this is divalobenzene. Okay, and then this is styrene structure. So you can see that. So it used the polymeric matrix. So and it's we can say co-polymerization because two of them, right? Co-polymerization. So styrene and DVB, and the amount of DVB get involved. So in this reaction kind of determines the degree of cross-linkage. Determines degree of the cross-linkage, and therefore so it kind of determines so the pore structure. That means more DVB added, more DVB get involved in this polymer, and the higher degree of cross-linkage. And then so that means the smaller the pore size, right? Okay, so it really determines that. So and cross-linkage, because cross-linkage, so this one kind of so gives well-defined pores. And so that's why this one, for the scissors one, you can manipulate that one. So its pore size has a much wider range than the silica-based particle. Remember, silica-based particle only like 40 to 2,500, but this one can be 100, not 40, 100 to what? To 10 to the 6, 10 to 6 much larger than 2,500, right? Okay, so because you see, because in this one, when you make the cross-linked polystyrene divalent particle, it's possible to make the macropores. For those macropores, the size can go up to 10 nanometer for the pore size, and then you're able to handle those very large cell molecules. Okay, so this is that's kind of a broadened application of this kind of matrix, the reason for the SEC. Okay, so advantage, already know that it can handle so very wide pH range, much wider so than silicon particle, so basically stable between 0 and 14. So, but disadvantage again, so we mentioned that earlier as well. So it's relatively soft, right? Okay, so relatively soft, it's not so rigid. So it may not be able to handle so very high pressure. So it has pressure limits. And also because of this aromatic ring here, so many of the aromatic ring here. So it has, the surface itself has some hydrophobic so property. So it's easy to have the hydrophobic interaction. So with those, like say polymer, so having a similar structure. So that's why we say, if you want to reduce this one, you can use the mobile phase. We say it's chemical related to the stationary phase. We can use in some, say for example, the toluene. Can use toluene as mobile phase to reduce so this absorption effect. Okay, so this is what it can do. Okay, see, and this is the something that shows a typical commercial column set, although it shows the molecular mass correspond to 10 Dalton, okay, 100,000, 10,000, so on, but actually it corresponds to different pore size. So we always have to keep in mind. So separation is function based on molecular size, okay, and therefore it's indirectly to molecular weight. Okay, so now you can see separate different so column. So and because of the pore size, like so this one, it deals with 10 to 1,000 molecular weight. So that means it must have smaller, very small pore size. For this one deal with 10 to 6 to 10 to the 8th. That means it has macro pore, right? Okay, you just basically you just choose the one that can meet your requirement. For example, let's see an example here. So here, so which column would you would be suitable for the separation of the mixture described here? So this is the some of the polysaccharides, so the sugar compound. Let's take a look. Starch, very large molecular. So that means the one totally get excluded. Don't bother to think about it. So how about for other sugar compound? So they have molar mass ranging from 122, which will be the first or last to come out. The last, right? Okay. So and to 1,153. So that means the molecular weight is between 122 to 1,153. So which one should we choose here? You type your answer. According to this molecular weight, which one should we choose here? You can type your answer in the chat room, in the chat box. Which one? Which one do you want to choose according to the molecular weight range of the polysaccharides we just talked about? Anyone want to pick one? Look at each one. Look at the range. Okay, so I already see answer. Yeah, okay, you guys get different answer. We want 100, more than 100. The smallest one is 122, right? The largest one is how much? Largest one is about 1,000. So you want to separate something between 100. Here's 100. Here's 1,000, right? Okay, you want something like, at least I say here and then here. So which column fall within this range? Which one? Which one fall within this range? Now, did you see that? I already got the correct answer. Yeah, someone already gave me the correct answer. Very good. I got more correct answer. Very good. Very good. So 500, this one, right? Okay, so we just choose the one so they can fall with it and then can do the separation. Understand? So this is how easy you can do. So you can get this information from the column menu you got from the manufacturer, and then so you can decide. Okay, very good. So, and already talk about, so, and based on that, we talk about the stationary phase, we talk about the mobile phase, and then now we just summarize that. Mobile phase must be a solvent in which the sample dissolves well, okay, completely dissolve it. It needs to be like in a relaxed form, because many of the polymers, actually they're the kind of the shape inside solvent is like the Randon coil, like this one. So if it's kind of the solvent, if nervous, it will really shrink. And if it's like, say, more relaxed, it will be more relaxed form. So you want it to be the relaxed form, dissolve it, okay? So, and also the mobile phase should be compatible with the stationary phase. That means like, say, polar, aqueous mobile phase, so matches those hydrophilic stationary phase. Okay, organic mobile phase matches hydrophobic stationary phase. So that's why now we can fill in the total, more complete information. For geofiltration chromatography, handle water-soluble sample, such as proteins. So it is the one that use aqueous mobile phase with our strength not really high, right? Okay, so because it's aqueous mobile phase, which is polar, so it has to compatible with stationary phase. So stationary phase also need to have some hydrophilic packing, so which is a porous silica-based particle. Got it. And then for geoformation chromatography, so because it deals with those relatively non-polar polymer, which is soluble in less polar organic solvent. So that's why the mobile phase need to be organic solvents, such as THF for polymer, or such as, say, some other things like, say, so toluene for or methyl crystal for that polyimide, so that's the things. And also, like, because your solvent now is hydrophobic, so the packing should be hydrophobic as well. So you want to use the polystyrene diphenylbenzene resin for that. That's it. Okay. So, and then for geoformation chromatography, this will be the one we focus later on, because we're going to talk about how we can use it to determine the molecular weight distribution of synthetic polymer, because their mass can go up from few hundred up to a million. So if you want to identify the mass distribution, so you have to have, so the column also have the pore size able to have such a wide range. Okay, so this is when you choose the sample, choose the solvent, and also think about the stationary phase. Okay, good. So then this is how it looks like. So if you want to apply this one, apply the size solution chromatography to determine the molecular weight distribution of the polymer. So then first thing for you to do is to do the calibration. Oops, sorry. So why we have to do the calibration? The calibration is to what? The calibration is just try to, because separation based on size, separation based on molecular size. Okay, and we already know for the elution profile, we get VE. This is what you can get from the instrument. You get VE, you get the response either for UV or either for mass or mass-based, so it's concentration, or I can say, really don't want to confuse you guys, like mass spectrometer. No, it's concentration. Like that one, is it UV response or concentration? So that response. So this is what you get. Okay. So, and you want to build a connection, not VE for that one. You want to build a connection. Okay, so according to the VE, because you told me, you say, so large molecule comes out early, smaller VE, smaller molecule comes later, larger VE. I want to build a connection between VE and molecular size. So calibration is build a relationship not between VE and the response. No, it's try to build a connection if we want to measure the molecular weight distribution. Okay, so try to build a relationship between the retention volume and molecular size. But here, because you aim to talk about molecular weight, because we say for the polymer, the molecular size increase, molecular weight increase as well. So you can relate that indirectly to molecular weight. So that's why we say we want to build a relationship between molecular weight, okay, and elution volume. Okay, so you want to do that. So in this chosen point size, so column, and then so later on, then you later on when you know to measure some sample, you got the VE, and then using calibration curve, you can know what is the molecular weight. Okay, so typically, so you will use some sample to do that. So you can see the polymer again. So we use this one. So we use the polystyrene. So as oligomer as example, this is we say elution profile of the styrene oligomer. So it has n number from 1 to 14. Okay, we take it as example. You can see that. So here, this is the VT, the total VT. Okay, so and this is a V0 here. So that means the largest one, V0. So we have seen multiple peaks, 14 peaks. Okay, the largest one comes out first. So this peak corresponds to n equal to 14. So that would be the largest. And then so this peak corresponds to n equal to 1. So this is the smallest one if n equal to 1 to 14 for this one. And then so this is equal to n equal to 1. Okay, so the smallest one. So 1 to come out. So what you need to do is, like I said, if you want to use it to calibration, you get a known series of this polystyrene. You know the molecular weight, you know its size, okay, you know which one is which. And then so, but however, you want to know, so when is the end of the elution. So you have to have someone, so that's large enough, it's very large. So, and so then it's totally excluded. So it indicates the start, okay, it's V0. Okay, so also you want to have someone so that is very small. It can diffuse in all the pore size. So, and then so the volume ticket is the VT, that's the end of the separation, right? Okay, and so, and also you get several ones in between. So same as when you do the concentration calibration, right? You want a large concentration, you want a smaller concentration, and you want several dots in between, right? Okay, this is quite similar. It's quite similar, but relationship is different. Okay, so when you do the calibration, you will find out what? You will find that x-axis is still VE, okay? But y-axis now is the log value of molecular weight. Now it's the log molecular weight, not directly using molecular weight. It's the log molecular weight, okay? And it has a shape, something looks like this one. Interesting. So we'll come back again. So, but this is a kind of 90-degree Z shape, okay? So, and this area is the one actually we are going to use for the calibration. Okay, so we'll come back and see how exactly that is constructed. Okay, so first, when you are doing the calibration, so the column is calibrated with a set of narrowly distributed standards of no molar mass, like this one. Okay, no molar mass, narrow distributed. And as a means to find out elution volume for specific molecular weight. So different ways for us to do the calibration. And most common way, we use direct standard calibration. What do I mean? That means the standards you use for calibration is the same polymer being analyzed. That means if you're analyzing polystyrene, you use polystyrene as the standard to do the calibration. So exactly the same, okay? And actually polystyrene is most commonly used one, okay? So that means you want to use the same one, then use the same standard. So then the molecular weight you get it will be the true molecular weight. But how to choose the size? We have to choose, so the molecules must include one that is completely excluded, because you want to get V0, okay? So also you want to get one compound completely penetrate the stationary phase. You want to get small one, so that is VT, okay? So very interesting actually. So normally what you can do is you can put something like as small as solvent. You can put something that's very small. You can put methanol, right? So this is methyl molecule that's small enough, because this is opposite to any of the chromatogram. Because like for any other chromatogram, the solvent is the first to come out, right? Solvent molecule is first to come out. But so this one, there's a molecule as small as solvent first to come out. So, but here, no, here, like say the solvent just goes through all the pore size. It'll be like say the loss to come out. But anyway, so you want one compound completely penetrate, and you want several compounds partially penetrate the pores. Okay, and then you can get that straight line of log molecular weight with retention BE. Okay, sorry. I don't know why. Okay. So, and that would be a series of commercially well-defined size and molecular weight polystyrene used. But of course, you can have so all the standards well depending on what you're analyzing. As I say that you want to have the exactly same as what you are studying. For example, if you have the PMMA, so let me show you here. So if you have, you're analyzing the polymethyl methylalkyl, and then so if you're analyzing the PMMA, the standard you want to use is PMMA instead of polystyrene. If you are analyzing the polycarbonate, the standard you want to use is polycarbonate. Okay, if it has its authentic standard, use that authentic standard. Okay, so and then that will give you the true value. Why? They won't tell me why. Why exactly we want to use it? Because it's based on size. Based on size, not really say molecular weight. Because the different polymer, they can have different what density. What's for example, some polymer like this one, it's a coin. Some polymer may be more like say tight coin. Some may have something like a rod. Okay, something may have very rigid sphere. And all of them have different density. Say even for example, so this one, this is a size, right? You can have the radius, right? Okay. So if I have this one, something like this one, so more tightly bent, but it can have the same size as this one. The two can have the same size. If I have the same size, that means they have the same VE. But obviously, which one is heavier? This one. This one has high density. It has larger molecular weight. So like if you're using the one on the left as a reference, as a standard to calibrate to the one on the right, you get a bias, a huge bias, because different compound, so they have this kind of the different conformation, because the relation between molecular size and molecular weight really depends on the conformation. So they have very rigid one, they are tensely coiled one, or randomly relaxed coil one. So they all matter. Okay, so that's why. So we just know that for certain type molecular size, for each type them O, so molecular size increase, molecular weight increase. But the rate at which the molecular size increases molecular weight varies for this different type of sample conformation. Understand? Understand? Okay. So for example, if we're using same, you have 10,000 delta and Dalton polystyrene, and you have same 10,000 Dalton, so PMMA. You say, oh, okay, same molecular weight, should be same size. Wrong. Okay, so there are two different kinds of things. So they will have even they're in THF, the same solvent, and then the size difference can be 20% different. Okay, understand? Because they're different compounds, so they have different this kind of density, size, molecular density. So that's why it's better if you analyzing polystyrene, use polystyrene as standard. If you cannot find authentic standard, so if you have to use polystyrene for the calibration of all the kinds of polymer, then the molecular weight you get is relative molecular weight. It's called the relative molecular weight. And you have to, in your molecular weight, you have specifically mentioned that this is polystyrene equivalent molecular weight. Then people will know that this molecular weight is not obtained from the authentic standard. It's obtained by using polystyrene as the surrogate standard to do the calibration. There will be bias. Understand? Okay, so keep that in mind. So separation based on the size in the solution. So, and for different conformation of the dissolved solute molecule, so they will have different density. Okay, so the different composition density. So that's why. So that's why you want using the authentic. If you want to get true molecular weight, so you want to use the authentic standard to do that, based on size solution, not molecular weight. So, and because for many of the polymer, so they have the kind of this structure like that one. So the random coil structure. So that's why. So we can relate its size to this molecular weight mass by this equation. So its radius gyration is proportional to this molecular weight. And the alpha is a constant that depends on the solute composition, the density we just talked about. Okay, so which type, different conformation. So the temperature and the solvent, that means what? Even the same compounds, polystyrene. So polystyrene may have different density. So in THF and in toluene, okay? So that means when you're doing the calibration and analyze, so you want to use the same solvent for the calibration and for the analysis. Understand? Okay, when your real sample, for example, using the polystyrene in THF for the calibration, when you're doing the analysis, you also want to use the sample in THF to do the analysis. And also the temperature is very important as well. You want to keep the temperature, okay? And also concentration. Actually, concentration also play a role. Concentration matters as well. So when you're doing the analysis, you want to use a diluted sample, diluted sample. You don't want to use a very high concentration because high concentration causes trouble. So and then so you may get the result, then so also get biased. Okay, so that is something you have to keep in mind. So even you have to use the surrogate if you cannot have authentic standard. So try to use something that's chemically. If you don't have authentic standard, using something like chemically and structurally alike, okay? Alike to as a surrogate, okay, if you don't have it. Okay, so so even for the same type, we can see that the true molecular weight so can only be obtained when the sample is the same type as the calibration standard, same type. And you even for the same type, for example, if you're using some polysaccharides, okay, and then you can see that even for the same type, it's the straight linear chain or branched that can make mistake, can make bias as well. This is an example show that. So large deviation from the true molecular weight occur for branched sample. You can see that this is a linear one. This is a branched polymer. So they have exactly same molecular size. Okay, they're same size. They have the same hydrodynamic volume. But because this one is branched, so it's more higher density. So like its molecular weight actually is higher, larger than the linear one. If we use the linear one as the standard to calibrate, to derive its molecular weight of the branch one, so you cause bias. You underestimated the molecular weight, right? Okay, so this is something just that you know. So something you have to put in mind when you are using scientific chromatography to do this calibration and to derive this molecular weight distribution. So it's very critical for you to pick up the compound that you can do for the calibration. So this shows us so many of the polymer available for the calibration. So and in organic soluble one, so the most common one, the polystyrene. So it has different molecular weight range. You can just pick up the one like say with your requirement. PMMA is also a pretty common one, and also B. So PBMA, this one, the polyambutyl methyl acrylate is also quite popular. So and also the nylon and then polyisobutane, this one. So you just pick up the one so you need to use. Okay. So and for the aqueous soluble one, so you can see for the aqueous soluble one, and it's poly methyl acrylic acid. So and also the propylene glycol, and then so polysaccharides. So dextran is cheaper. Okay, and this one, so it's branched one. So you have to pay attention to that. So and anyway, so now we can see that. So now you have to use one that's large enough. So totally get excluded. Okay, what does it mean? Because if you get something like large enough, totally get excluded. So, and you know its molecular weight. So because this is actually a exclusion limit, I mean, as long as your molecular size is larger than certain value, for all the molecules larger than that, they're all excluded. They're all eluted at V0, right? Understand? So that's why here as a straight line, because it doesn't matter. So this is already the upper limit. So if your compound is larger than this one, or molecular weight larger than that one, so they are too large to get diffused in. So that means all of them, so they just like say totally excluded. So they will be like in V0. So that's why. So you have this VE and you have this log molecular weight attribute. Okay, so first one, I have something really big. So I got one dot here. Okay, so totally excluded. So this corresponds to V0. Okay, so in my calibration curve, I also got something like really small. Okay, for anything smaller than that, so they got the same elution volume, which is VT. So then here, I got something like here, I got here, and then so that corresponds to VT. So, and then I got something like say in between. Okay, so I got something like say it has its BE, so BE1, oops, and it has its log molecular weight 1. I have a second point here. So all my standard, okay? I already have 1 point really large, 1 point really small. I have another second point up here. So that is correspond to VE2, and that is molecular weight. So molecular weight 2. Okay, and we got 3, and number 3 and number 4. Okay, so this is what I get. They say they're not really a straight line. Yes, I know, because don't you now V0 and V2 definitely are not on the line, straight line. So here we got straight line for those in the middle. So I can draw a straight line. Then what you do is that you draw a straight line across them. Okay, you got straight line. See that? And then, so because for V0, it's like say, as long as your particle, your analyte is larger than a certain size, whatever, so molecular weight, molecular size larger than that, they all get the same V0. So that's why it's a straight line, right? And also same for VT, you got straight line. Anything smaller than that, same. So that's why. So, and here now you got two cross points for this straight line. And let me go straight. So, and this straight line here, so will be what? Will be the up limit of the molecular weight. That means the molecular weight, that molecular size that be get excluded. So that's why it's called exclusion limit. And here, this one will be the molecular weight or molecular size is smallest that can diffuse everything in. So that will be the permeation limit. Okay. And so the range of molecular size or molecular weight, so that can be separated, will be between exclusion limit and permeation limit. Okay, and this will be the area that you can do to identify, do the calibration, and then use to identify so the molecular weight, okay, of the unknown. So for example, if you have some sample, if your sample with the volume, if the V of your sample is larger than if it's same column, sorry. If Vs of your sample equal to Vt, oops. Okay. If the sample volume, elution volume equal to Vt, can you use the calibration curve to know its molecular weight? Can, yes or no? If the elution volume of the sample, Vs, equal to Vt, can you know? Can you use the calibration curve to know its molecular weight? No, right? Okay. So of course not, because like anyway, so it's because we know that as long as it's like small enough, so it's Vt. But if it's like something like your sample volume, elution volume equal to V0, can you know its molecular weight? The answer also no, because this just represent, okay, it's large enough. It's large enough to get totally excluded, but I cannot know which one it is. So you can only know the molecular weight of your sample if the sample volume is larger than V0 and smaller than Vt. And then, so it will be fall within those areas. For example, if we know that VE, your V sample is here, you get it up and get it here, and then you can know the log of the molecular weight of your sample. Understand? Now, do you understand now? Okay, you see that. So this is how it looks like. Okay, so later on we saw, let me show you this one first. So this is how it looks like. So you run the calibration. So this is V0 and this is Vt. You got that Vt and you got that V0. Okay. So, and this is calibration for correspond to those points. Okay. So, and now you have your unknown sample, but you know the V sample, Vs1. Okay. You know Vs2. Vs1, Vs2, Vs1, Vs2. You get Vs, uses calibration, and come here, you get the log molecular weight 1. And here you got the log molecular weight 2. Okay, so you have to fall within, so V0 and Vt. Got it? Understand? So then that means when you choose the column, so you have to make sure. So, and you simply can fall within that. So that's why, so the first example, they're here. So from the polysaccharides, so you know, you got some idea. So estimate the polymer, probably know what kind of range should be. And then so you check the manufacturer so instruction so of the column, and then so you know so which column so you have to so pick up to do this kind of the thing, analysis and calibration. Okay, so so far okay. Now you understand how to do that. You understand? Okay. So and then so that's it. Okay, so and there's several things that you have to pay attention. So while you do the calibration, so since now is the 8:55. So how about we take 5 minutes break? We'll come back at 9 p.m. Okay, so 5 minutes break. Okay, so guys, we'll start again. So you see, for the calibration of the size solution chromatography, and so we need to use fresh solution of standard. So and that means you prepare that, and the calibration solution should be as dilute as possible to avoid any concentration effect. So and because it's too concentrated, so the compound will not be really relaxed. Okay, so and more shrinked away. So and also the concentration effect may cause the increase of the some of the retention time, and if it's too concentrated, so it becomes a clog the colon, so something like that. Okay, so we can see the for the polymer sample. So sample must be dissolved in a solvent, same as used for that mobile phase. So this is ideal case, but sometimes it's a bit different. It's fine, except for some special case. A good solvent can dissolve a sample so in any proportion in a range of temperatures. Okay, so the solvent is very important. And the rule of thumb to prepare the solution, you can see for different size range. So, and for the smaller size, medium size, or for very large size, basically, the larger the size, you want to make it even more diluted. Now for this one, if we think about it's in, if we just give it like say 1 gram per milliliter, we know that for the organic solvent, it's not really 1 gram, but will be smaller than that one. So, but anyway, so if it's except for DCM, so if it's 1 gram per milliliter and you times the 0.1%, which assume that, and then so that concentration will be like say 1 milligram per milliliter, right? Okay, so that means say it should be diluted. It should be less than normally 1 milligram per milliliter. So for that one, for that kind of concentration, you can see, and then here, so and for a relatively larger one, so even smaller, more diluted, it's 0.5 milligram per milliliter. For even larger one, so it's even smaller, it's 0.25, right? 0.25 milligram per milliliter. So, and a calibration column, when we use that one, of course, and after you prepared, especially those large ones, you also maybe want to say filter that. And for the calibration column, they can be used for extended period of time. So if the column is kept in good condition and not allowed to dry out, and you don't want to like keep the column at extreme temperature, very hot, no. You also don't want to like shake it vigorously, no. So this is something, if you can maintain the colon, keep the colon so carefully, treated carefully, and then it should be used for longer time. And for the molecular weight determination, so and the molecular mass of unknown fraction can be determined by comparing the sample chromatograph with calibration curve, as we see that one, compare with this part. Okay, so and once you know that VE for the sample, you put that into this chromatogram. So, and you can know the molecular weight of the sample. And different type of molecules may have different mass density. So for example, the so amide and polystyrene, they are different. So that's why I keep saying that. If you can use the same compound for calibration, so if the standard used for calibration is same as your analyte, that is ideal case. That is what you really want. And then so you can get so this one to be on true molecular weight, right? So because for different conformation of the molecule of the polymer, so they have different density and then so mass to size ratio. So that means the rate for the increase of the size together with the molecular weight could vary for different compounds. So even the same molecule may differ in size in different solvents. So that's also what I mentioned earlier. I say use the same solvent, same condition, same temperature. So for calibration and for analysis, okay? So because most of polymers, so they're in the random coil, so that's format conformation, the coiled molecule may swell, relax, or shrink. Okay, so and the solvated, they could be solvated in one solvent and then so remain unchanged in another. So this is really the solvent really so influence. So they are kind of, they say, condition. And then so if they swell or shrink, definitely size is different. And if size different, doesn't matter, it's molecular weight, right? So the VE will be different, right? So we have really good control of temperature, but temperature really so influence. So that's size. So that's why. So that's why you see that earlier mentioned that for the pump, you have to really so thermostatic that control the temperature. And also we need to have very precise pump. Now you guys do know why we have to use very precise pump now? Why? Now do you get the point? Do you get the point why we have to very precise pump? Because the pump get what? Flow rate. Flow rate times retention time, so that corresponds to retention volume. So the pump accuracy determines the accuracy of which one? Of VE. So why the accuracy of VE matters? Because now VE is related to what? Look at this calibration curve. VE is proportional to what? Log value of molecular weight. If there's a little bit difference of VE, because that's log value. How to calculate molecular weight? 10 over VE, right? So that will cause a small difference of VE can cause a good big bias of the molecular weight, right? So that's why. So you want the pump to be quite precise, and then you have more accurate reading of VE, and then you have more reproducible reading, and then so you can have a more accurate measurement of the molecular weight. So that's the reason for that. Understand now? Okay. So and now also temperature control is because we want pump head and colon thermostatic to 0.1 degrees C. Okay. Okay, so we have seen that. This is how we determine the molecular weight of unknown polymer. And then so how sometimes because that we say the capacity is limited. It has limited capacity. Then how can we improve the capacity? How can we improve the capacity? How can we improve that VI resolution? So we can put the two or more column of the same type together. So you can see here, so if you have two columns together, so you got the VI doubled. So that's why, so it's have the V, that caused elution volume. So of course, then be elution or volume, so it could be doubled. So that's why you can see here, now it's less than 10, now you move to here. Okay, but at the same time, so because more space for it to differentiate from each other, right? So that why you can see a better, so a better what? Resolution, right? You can see a better resolution. So, and if you separate compounds with really great molecular mass range, for example, so if we got something from about 100 to 10 to the fourth, if I get something like say 1 to 10 to the, say, how about not to 10 to the fifth, I got that one. So, and which column should I use? If the molecular weight is from 10 to the 20, 100 to 10 to the fifth to here. So which column should I combine together? So this one, 500 angstrom is no longer so enough. So I can combine 500 and 10 to the fourth. This one, I can combine these two together, right? And then so I should be able to cover that range from 10 to the second to 10 to the fifth, right? Okay, do you see that? So this is how we do it. Okay, so you can combine them so together, and then so you can extend so the ability for them to handle a wider mass range. So, and then a very critical part of that is also preparing the sample, because this part can be the rate determining step, because then saying you typically you handle with those macromolecule, you handle with the polymer, you make them dissolve, and it's a bit challenging. Okay, so the polydispersed one, so normally you have to weigh like 25 to 100 milligram. For the monodispersed one is about 1 to 20 milligram for example for the protein. So, and also we say the solvent must allow polymer chains to open up in the most relaxed conformation. So then later on you measure, get less bias, but do not use any deforming agent. So example, do not using urea, no, because they're going to transfer the protein to a random configuration, so reduce the structure difference. Okay, so and this is something like don't do. Okay, and you have to be patient to allow sufficient time for the chain to unfold. It really depends on which compound you are handling. So it can, the time difference can be 0.5 to 24 hours, and it could take more than 3 hours for some polymers. Okay, so normally, so the greater the molecular weight, the high degree of crystallinity, the longer the time it needs for it to unfold, for it to be like opened up in the most relaxed conformation. Okay, so if something like say very hard to dissolve, and then very highly decrystallized polymers, so you may want to use some temperature so to help it, but do not really use like say too high the temperature. Okay, so but with caution, but you have to see whether that really can influence or will change so the molecular weight distribution or not. So normally it's about say 130 degrees C to 150 degrees C. Okay, so and also the polymer solution to be filtered unless they otherwise will be a chance to shear, and also to enhance the dissolution, some very light swirling could be done, but do not vigorously shaking it. Do not ultrasonication. No, because that will say shear the polymer. Okay, so and also to narrow stand solution need not to be filtered, but and also the high molecular weight stand should not be shaken at all. Do not, because they make it break. So, and using the solvent again, say the solvent use should be good mobile phase, should be the one so that can really make your sample dissolve that completely. That's very important. Keep that in mind. Normally we use THF for polymer. So, and for those polyamide, and then ester can use a little bit polar one, can be the cresol, and also you can generally heat it at maybe 90 degrees C should be fine. Okay, that's something like say mention about it. So for detectors already mentioned, so can be absorbance, can be UV visible. Is this UV detector is widely used. We normally use 280 for protein, and so this is due to absorption of amino acids, and use like 254 for other compounds. Okay, so and however the limitation, as I mentioned already, many polymers they have no chromophores or other detectable properties. So what can you do? So you have to use more universal property. So and then so that one can be what? That one can be mentioned about, can be say mass-based or some other say refractive index based. For the mass-based, we use the light scattering. We use the light scattering, and the light scattering of that one is actually based on its concentration. So that's one is related to the mass. Okay, so and for refractive index, we can see so for mass this one. So light scattering is Rayleigh scattering light intensity. That intensity is proportional to its concentration. And for the refractive index, the change in the refractive index is say related to or the concentration of the analyte shows up in the sample solution as well. Okay, So let's take a look about this differential refractive index detector. So this one we actually already mentioned a little bit. So you have to have the light source. So it can be LED light or incandescent light. So it shoots through the sample cell and the reference cell. So if there's no sample, so the sample cell, reference cell, so they are same. So the light, so just shoot on a detector. The detector has, so the photosensitive surface is photosensitive surface. So and then it can measure the position so of the light being like shooting on it. So if there's some sample so in the cell, so what happened is then now so the refractive index changed, right? Okay, and what happened is that the light beam after pass through the sample cell will be bended. So when it's shooting on this photosensitive surface, and then you will see the shift the distance from original space, the spot, and then so that this one, sorry. So this distance, sorry, the x. That distance, like the shift the distance, so responds to the change of the refractive index, okay? And then we can see that actually the higher difference between the refractive index of the sample and the eluent, the more intense the signal, right? The more intense the signal. And then so the sensitivity is not really that good. It's normally say just go down to 0.5 microgram per milliliter. Okay, so we say it's a universal but blind detector. So and it's not really that sensitive. And also earlier we say that it's not good for gradient illusion. But anyway, so for here, the seismic chromatography is not really a big matter for that. Okay. So another one like we mentioned about earlier is for evaporative light scattering detector. It's also a universal detector because it's also corresponds to the we say the property of the whole mobile phase, so including the sample, right? So it's a response does not depend on the optical characteristic, although it say it's light scattering. So it's not really optical characteristic. It does not require it to have any of the chromophore. Okay, it does not need to absorb the light. It scatters the light. So and any non-volatile compound, so it doesn't matter it's chromophotic or non-chromophotic, can be detected. That is good for polymer. But polymer is really large, so they are not volatile. They are non-volatile, right? Okay, good. And the response is based on mass and the amount of light scattered. So, and not really extinction coefficient or refract index difference between the mobile phase sample. No, it's just whatever the light scattered. So it's really basically on mass. So how much of the particle shows up there, and then how much light can be reflected or scattered. Sorry. So it provides a more accurate representation of the actual mass concentration. So and make it really good. So ideal. So for this purity analysis, and then so but it's limited to volatile mobile phase. That's fine because when we are using the polymer analysis, the organic solvent we use is relatively volatile, easy to evaporate, and then so and also the polymer is quite heat stable, right? Thermal stable, and the polymer is really non-volatile. So so the mobile phase can be evaporated. I showed you guys this one before, but which we go through the first one. So what comes out from SEC together with the mobile phase and the polymer inside. So the nebulize, they get into a nebulizer, and then the colloid effluent just like pass through a needle, and the pressure the nebulizing gas applied, and then so then that is nitrogen gas mixed with that nebulizing gas and form a dispersion of the fine droplets. So then the fine droplets, they were going to pass through a heated drift tube. Heated because you want to evaporate the solvent, right? So the mobile phase just evaporates. So what they leave is just leaving very fine mist of the dried sample particle. So in this solvent vapor. So now it becomes solid, become dry particle. And then dry particle pass through the flow cell until they come to the bottom. So the heat a laser beam here. So the laser beam, the light being hit it. So the light scattered in all direction, So, and you can put, also we can put the detector at about 40 degrees C, 45 degrees C, about 45 degrees to that. And it actually formed with just a pair of the optical fiber and also the filter, optical filter. And then so when you pass through optical filter, the light pass through that optical filter. So and then so optical, then so that will be like say collected by the photo multiplier. Okay, so and then transfer that to signal. So overall we have this one actually. So and you have the signal. So the signal response, that means the amount of light scattered. So it's related to the mass by certain relationship, like A equal to B mx order. So A, this one, is the peak area you get from the ELSD. And then M, that is the analyte mass. So it's the analyte mass. So how about B and X? So for B and X, so there are some coefficients. So that depend on, there's some just a coefficient that depend on, they just depend on both what? Both the analyte for sure, right? And what? Both the analyte and also the operation condition. So that is that one. So if we want to build a relation before A and M, how to do that? How about we take a log of both sides? Log A equal to what? I switch that one. Okay, equal to what? X log mass, right? Plus log B. So now we get the linear relationship of log A proportional to log molecular. So the mass. So you get that linear relationship. So you can start with the lowest mass. So and go to that one if you want to measure mass concentration like that one. Okay, so this is how that so related. Okay, so just for information. So and you can see like we can apply so size solution chromatography to many different fields, not exactly to be just like say the polymer, so molecular mass distribution. So we can, even for some sample treatment, we can remove the high molecular lipid from food sample extract. So you can see here, so this is a blank chicken extract, and then the second one is the blank chicken extract. We spike the target, and then so depending on the size, and then so we can just like say exclude that. So and also, and this one is analysis of synthetic polymer about their molecular weight, because each one want to monitor the aging of the polymer. So, and this is the new one, and this is the aged one. We can see that the aged one, the molecular weight already decreased. So remember we mentioned that earlier. We said for polymer, they need to have enough high molecular weight to keep this physical property, right? Keep its physical property, keep its transformation temperature, like that one. So from here, you can see, so they have 4 columns, right? You can see they have 4 columns together. So that definitely corresponds to different point size. I say by combining 4 columns together, so expand the molecular weight range that can be analyzed, right? So, and the particle size, a mobile phase is 1 milliliter per minute. So the chloroform, many chloroform with 2% of hexafluoroisopropanol. Okay, and temperature, I use UV detector at 254. So this is very typical, very, very typical. So condition for that. And this is a calculation of sample of biological origin. So this one for sure. So we can see that this is our biological origin. So it should be more water soluble one. Okay, so it will be gel filtration. So no wonder, so that's why. So it used the stationary phase is silica based, porous silica based particle, which is 10 micrometer diameter. And then so you can see the pH about 4.6. And the mobile phase, again, so this is no wonder, it's a buffer solution, aqueous buffer solution. So with some of those sodium, so phosphate, sodium chloride, and so on. So because it's a protein, to monitor those proteins, so that's why I use 280 nanometer, okay, because that's caused by amino acid absorption. And then by doing so, so you can see high molecular weight protein, so this one probably is totally excluded B0. And then so, and have also things 2, 3, 4, 5, right? So that's correspond to so different molecular weight. See, this one 3, 2 corresponds to 150,000, and then 5 corresponds to what? 5 corresponds to 16,500. Okay, so this is almost 10 times larger. So 10 times, say, not larger, molecular higher than that, 2 is. Okay, so if we want to summarize, we can see that, already see the application. If we want to summarize that one, so all injected molecule, so they are eluted as long as no unwanted absorption effect occur. So in the size solution chromatography. So as long as they dissolved, as long as no unwanted absorption, all injected can be eluted. So it's quite predictable. The breakthrough time or breakthrough volume represents the completion of the chromatogram. Therefore, so the separation time or the total volume used can be predicted. The elution volume or time is a function of molecular size, not really molecular weight. So, but for the polymers, because their size increases, when the size increases, the molecular weight increases. So, therefore, the elution volume is indirectly a function of molecular mass. So, and therefore, the size solution chromatography can be used for molar mass, molecular weight distribution, or for molar mass determination of the unknown compound. But you have to do calibration. And when you do the calibration, so the perfect way is to use the standard you use is the same as the standard you analyze, the compound you analyze. So, and as the separation is completed after only a small amount of mobile phase, so it has passed through because it's VT minus V0, that is VI. VI indicates the capacity. The peak capacity, so it's limited. Because it's very limited, mobile phase volume can used to elute the sample. So the number of peaks that can be separated from each other within a specific resolution is limited. And for most compounds, they have to at least 10% of molecular weight difference to be separated. So, and 2 types of molecules can be separated, provided that there's at least 10% difference in the molar mass. That corresponds to size, right? Okay, and peak do not broaden as the retention time increases because there's no interactions with the stationary phase, and so a very limited broadening. Okay, so and in contrast to other method, molecules are promoted to reside in the stagnant mobile phase because you have to get the advantage of that if you get VT, right? Okay, so the molecules they wanted to diffuse into the pore size, and they can get different paths to come out, then they can be separated, right? Okay, so it is wanted so they can diffuse into the pore. Okay, hence therefore the plate number are generally lower than normal found HPLC and actually not really follow the Van Diemen's equation, and because there's no that separation interaction, so there's no interaction equilibrium because everything based on the size. So hence relatively large amount can be separated. So that means that you inject the sample. So even it's less than 1 milligram per milliliter, so that is already so much larger than we normally handle. So in HPLC, Okay, so that's already 1,000 ppm, right? So however, the viscosity of the sample solution should not be more than double that of the mobile phase. So, and then because it needs to comes out together with mobile phase, okay? So as elution volume are small, a reduction of the actual column volume in all equilibrium, in all equipment, so you should become very important. You want to keep that extra column volume as small as possible, right? So then because that will cause your peak broadening, you will get to the detector. So advantage of SEC is short and well-defined separation time. So it's predictable and it has relatively narrow bands. So, and which can lead to good sensitivity. So, their freedom from sample loss because the solute do not interact with the stationary phase. And so also the absolute column deactivation brought about by interaction of the solute with packing. Okay, so limitation separation is by hydrodynamic volume, I mean size, rather than molecular mass. That's something you have to keep in mind. So that means the density of the different things that really matter, right? Okay, so that means that's why I keep saying about when you do the calibration, about when you're using a solvent and so on. So they're not really suitable for a sample with similar size. Not really good, not good for isomer because they're separating based on size. Okay, so they should have the different size difference. And for if we return that to refer to molecular weight, so at least a 10% difference in molecular weight required for reasonable separation. There's an upper molecular weight limitation for separation. So based on depends on the pore size for the stationary phase. That means if you have molecule larger than that, so they cannot be separated. They all comes out at V0, right? So only a limited number of bands can be accommodated because the VI is limited, right? So the time scale for chromatograph for this elution profile is short. And then so some broadening. Okay, so that's the end. So for this part. So and then let me see, because we have the today, okay, we have another lecture coming next week, right? So that'll be the almost the last lecture. So I'm not sure. I guess we can finish that one. So next week. So do you guys want to stop here, or do you want to like say, because we still have 8 minutes left, do you want to like start capillary electrophoresis, or do you say tired and then so we leave it for next week? Which one do you want to? So we can. So I talk a little bit. We can talk a little bit about start. Okay, how about that? So we just introduce the very beginning. Okay. So and I think that should be pretty enough for today. So we just like to say a little bit about talking about the introduction about the capillary electrophoresis. Okay. So the capillary electrophoresis is actually a relatively new technique. So and it was developed in 1980s. So and remember, I already mentioned that capillary electrophoresis. Can anyone, if you're not falling asleep, okay, anyone response? So we use capillary electrophoresis for analysis of what kind of compound? For what? For ions? So mainly for ions? Yes or no? Can we use that for ions? So capillary electrophoresis, remember I mentioned a little bit, the answer is yes. Yes, we actually can use this for ions, for separation of the sample ions. And the difference for capillary electrophoresis is like, say, it used for separation for ions, it can handle both cations and anions at the same time. Not like IC, ion chromatography, ion exchange chromatography, you have to use different column for cation and anion, right? Okay, so it's actually a very powerful, high efficient separation technique for sample ions. So, and if you look at this schematic for its instrumentation, this one, so this shows the typical schematic for instrumentation setup. You can see that the separation happened in a capillary tube, the narrow bone capillary tube, which is similar to that GC one, okay? GC column. narrow-bore capillary tube has the ID. So ID is typically 25 to 75 micrometer. Okay, so its capillary tube is happen here. So and what happened is like say we see the capillary tube, one end is in the source valve and the other end is in destination valve. So this capillary tube is filled with electrolyte solution. And the electrolyte solution, so they are the buffer solutions already put in this source valve and destination valve. Okay, so the ions migrate in this capillary tube. They're separated in the capillary tube. You may ask how? How they can migrate? How they can separate? Do you see a pump here? Can you see a pump? Yes or no? Can you see a pump? Anyone? This is a very straight one. No pump. No. Thank you for the answer. It's so straightforward. If it's no pump, what are the driving force to drive the ions to go through the column, capillary column? Anyone can tell me? Electricity. Very good. Thank you. So where does this electricity come from? It's the electrical field. Apply that. It's the electrical field. So that provides the driving force for the separation for the ions to go through. Because you can see the high voltage, the electrical field is applied on both electrode, so that located in the source valve and destination valve. And this electrical field is applied by high voltage power supply. Okay, so the high voltage power supply here in CE is like the pump. Okay, so in normal, so LC chromatography. Okay, so you can see electrical field applied between the source and destination valve, and then so that initiates the separation or migration of the ionite. So, and it is important to note that actually later on you see that all the ions, doesn't matter it's positive or negative, they all go through this direction. Okay, I think this, I'm talking about the very basic CE, very basic CE. We know later on we'll talk about different CE, but for the very basic CE, they all migrate from a source valve to destination valve. Why they say destination valve? Because the destination valve, the end, is very close to the detector. You can see that now the capillary is passing through the detector. Part of that is inside detector. And the end now is located in the destination buffer. And two electrode come here. And the destination buffer valve is the cathode. And then so in the source valve is the anode. So, and you can see that if you want to introduce the sample, so here is a sample valve. You just put the inlet, of the capillary into the sample valve. You can do this one, put for a certain time, and you can either apply voltage, or you can either apply cell pressure, or you can provide some siphoning to introduce that into the capillary. And then you put it back into the source valve and apply the voltage. Okay, so and so because then apply voltage and everything goes here, and then all the ions that migrate, they pull through the capillary in the same direction. That is caused by electro, so osmotic flow. That's something very important. So everything goes through this destination valve, the end detector part, by electro-osmotic flow. Then you may ask, how then can they separate? Okay, so they migrate and they separate due to the electrophoretic mobility. So the electrophoretic mobility is because they have different charge. They have different charge density. For example, it's very sure that then the ions, they're more attracted by the anode. And the cations, they're more attracted by the cathode. So then if it's on the normal condition, all the cations, they have the acceleration rate because they're pulling to the cathode is pulling them to the detector. But for the older ionize, so they are slowing down because the anode is pulling them back, right? So they're different. So they're separated. One have acceleration rate, one have the pulling rate, pulling force. One is have acceleration force. And also, even within all the ionized atoms, because they have different charge density, and the degree of pulling or degree of acceleration is different. So there is electrophoretic mobility that achieves the separation, and it's electro-osmotic flow that everybody goes to the detector. Okay, so I think that's pretty enough. That's just an introduction for that one. So now you got two new terms, electro-osmotic flow and electrophoretic mobility. So we see that, you hear that, or you see that again. So next week when we talk about CE. So, and then that is one of the very key terms in that. Well, okay, so I think that's pretty enough for today. So any questions so far? So if no question, so we're going to stop here. Okay, so I'm going to see you guys next week. Remember to prepare for the oral presentation. Okay, so because we're going to have oral presentation on April 6th, I'm going to upload the marking sheet onto BU in Moodle as well. So, and then so later on, so on April 6th, you guys have to also give marks to your classmates. Okay, so if no question, so bye guys. See you.